Here we have a stress strain graph for a particular material. Our vertical axis is our stress in units of newtons per meter squared, which is equal to pascals. On the horizontal axis, we have strain, which is unitless, and so our first step for finding the Young's modulus is to find the gradient of our stress strain graph. So the gradient is going to be where we have a linear section, because we want the gradient at our elastic region, which is here. So the 2 points we're going to use are at the start at 0, 0, and at the end of our linear section where we have a stress of 6 times 10 to the 7 pascals on a strain of 0.001. So now we have our calculations. We want to find the Young's modulus, which is E, which is going to be the gradient of our graph, rise over run. The rise goes from 0 to 6 times 10 to the 7, so the total rise is 6 times 10 to the 7, and similarly the run is 0.001. That gives us a Young's modulus value of 6 times 10 to the 10 pascals, and in a more useful unit we can change to gigapascals, which is 10 to the 9 pascals, which gives us 60 gigapascals. The second part of this question asks us to find the strain and energy per unit volume stored up in the material up to the point of fracture with working out. So as you should know, the strain energy per unit volume, or in joules per meter cubed, is equal to the area underneath the graph. So to find the area underneath the graph, we're going to split it up into 3 parts: a triangular section here, square section here, and for the purposes of our calculation, we're going to split this and assume that it is a triangle. So we're going to have our areas A, B, and C. On to the calculations now. The total area, AT, is going to be equal to the area A plus the area B plus the area C. The area of a triangle is equal to half times its base times its height. The area of our square is equal to length times the width. So the total area is going to be half times the base of area A, half times 0.001 times the height, which is 6 times 10 to the 7, plus the area B, which is the width, which is 0.0015, 0.0015 times the height, which again is 6 times 10 to the 7, plus the area C, which is half times the base, which again is 0.0015 times the height, which is 2 times 10 to the 7. If we put those into our calculator, we get the area A as 30,000, plus the area B, which is 90,000, plus the area C, which is 15,000. Adding them all up, we get our total area, which is 135,000 joules per meter cubed, which we can write in scientific notation as 1.35 times 10 to the 5 joules per meter cubed. And that is our area answer for the strain energy per meter cubed.